Here are some examples of problems involving the conservation of angular momentum. For a rotating object, angular momentum is defined as the product of its moment of inertia times its angular velocity. The angular momentum of an object can be changed by outside net torque through Newton's second law. In the absence of outside net torque, the change in angular momentum is zero. We refer to this as the conservation of angular momentum. For a single object, this sets up an inverse relationship between its moment of inertia and its angular velocity. In our first example, we twirl a ball on a massless string, then let looser so that the ball twirls slower. When reading a problem for angular momentum, pay attention to the variables of rotation, mass, and any geometry affecting the moment of inertia. Highlight what is being asked for. Start by getting expressions for or calculating moments of inertia. In this example, we must apply the parallel axis theorem for such calculation. In parallel axis, you must add the moments of inertia of the object through its center of mass plus the moment of inertia treating it as a point mass. Plug in with units if you can. Get an expression for the final moment of inertia as well. Apply conservation of angular momentum and solve for the unknown. Depending on the geometry, the algebra may take several steps. Once you have an expression, plug in with units and have your calculator compute the result. Reread the problem and make sure you have answered the question in a sensible way. As an aside exercise, you may compare this result with one treating the ball as a point mass. Note that the point mass treatment becomes more accurate the farther the object revolves around the axis. In our second example, we are going to drop a point mass on a rotating disk. Due to conservation of angular momentum, this will slow its rotation. Read the problem for rotation, masses, and radii. Highlight the unknown. Calculate or have expression for the moment of inertia from before to after the combination. Apply the conservation of momentum. Substitute in your expressions. Solve for the unknown. And plug in with units. If your rotational rates have the same units both in the beginning and the end, you do not need to convert those units. Reread the problem and check that your answer is sensible. In summary, for conservation of angular momentum problems, you must read the problem, get expressions for moments of inertia, apply the conservation of momentum, solve for the unknown and plug in, and then reread the problem to check your answer.